Both acids and bases come in a wide range of strengths. There are strong acids, so things like sulfuric acid, nitric acid, hydrochloric, hydrobromic, hydroiodic acid are all strong acids. Strong acids are characterized because they ionize or dissociate completely. In solution. Whereas weak acids, so things like acetic acid, which is in vinegar, acetic acid is a weak acid. It only partially ionizes in solution. It's at equilibrium in solution between the acid, its conjugate base, whereas HCl is a one-way road. It's going to go into solution and it's going to ionize completely. And so we'll talk about that in the next 2 slides. So for example, here is our HCl. HCl is a strong acid, so when it reacts with water, you'll notice that this arrow is just a one-way arrow. It's a one-way road. I put in 100 molecules, all 100 ionize and give me 100 hydronium and 100 chloride. So what would that tell you about the magnitude of K for this reaction? Would we expect K, so I'll just write it out, right? The equilibrium for this reaction would be the concentration of hydronium times the concentration of chloride all over the concentration of HCl, right? We ignore liquids and solids, so that would be the equilibrium constant expression for this reaction. For a strong acid, what would the magnitude of K be? Right, we would expect K to be much, much greater than 1 for a strong acid, because if it ionizes completely, we're going to have a large concentration up here and a very small concentration down here. So another way to characterize strong acids is that they would have a very large value for their equilibrium constant. Whereas a weak acid, so here's acetic acid or vinegar, that's a weak acid, and so you'll notice the difference here is that when it reacts with water, I don't have a one-way arrow. I actually have a two-way arrow showing that this can form an equilibrium. This process is reversible. Acetic acid can donate a proton, so here would be the acidic proton that it donates that to water. I form hydronium and acetate, but then the acetate can always go back, pick up a proton, and reform acetic acid. So this is a weak acid. There is an equilibrium between the acid and the conjugate base. I'll write out the expression for this weak acid. Right, all over acetic acid. We ignore that. And what would the magnitude of K be for this equilibrium, for a weak acid? Right, we would expect K to be much less than 1, because now I'm going to have a large concentration of starting material, right? This only partially ionizes. Say I put in 100 molecules and 98 remain acetic acid, and 2 of those molecules ionize to give me acetate, right? Now, for a weak acid, K is going to be much less than 1. The smaller the value of K, the weaker that acid becomes. We talked about water earlier and how unique it was, that it was amphiprotic, that it can behave like both an acid and a base. That also means that water can react with itself. If it can behave like an acid and a base, the two can react together, and this is called the autoionization of water. So one water molecule acts as the base and accepts a proton. So this takes a proton from that water, we make hydronium, H3O+, and then when this loses that water molecule, right, after we lose that proton, we're left with our base, the hydroxide in solution. So water is unique this way in that not only is it an acid and a base, but it can also react with itself. We can use this equilibrium to kind of figure out the ion product for water. Right, so the equilibrium constant for water, for this process, the autoionization of water, would be, normally, right, it's the concentration of products over reactants. And in this case, we can ignore both reactants because they're both liquids. So my equilibrium expression for this reaction is simply going to be concentration of hydronium times the concentration of hydroxide in solution. This is known. This is the ion product constant for water, and so we rename this Kc actually the Kw. The ion product constant for water, and we know at 25 degrees this concentration, or this equilibrium constant, is 1 times 10 to the minus 14. So we can actually use this equilibrium constant for water to figure out what is the concentration of hydronium and hydroxide. All right, so the expression would be Kw equals the concentration of hydronium times the concentration of hydroxide. We know what Kw is. Based on that, what would that make my hydronium and my hydroxide? All right, we haven't looked at a problem like this, so maybe that was originally hard to kind of figure out, but we know Kw, we know that is 1 times 10 to the minus 14. And now you're saying I've got two unknowns. I don't know hydronium, I don't know hydroxide, but if we look at the balanced chemical equation, for every one water that reacts with another water, I'm going to form one hydronium and one hydroxide. So I don't know either of those concentrations, but they are equal to each other. So if I say, well, I'm going to form X amount of hydronium, I'm also going to form X amount of hydroxide. So our Kw equals the concentration of hydronium, which is X, times the concentration of hydroxide, which is X. So I get 1 times 10 to the minus 14 equals X squared. Take the square root of both sides, and X equals 1 times 10 to the minus 7. So that tells me that my hydronium concentration is 1 times 10 to the minus 7, and my hydroxide concentration is 1 times 10 to the minus 7, all based on the autoionization of water. Now that we know the concentration of hydronium in solution, that's where we can find our pH and start to find our pH. So one small pet peeve is that pH is always lowercase p, capital H. It is not capital P, capital H, and it's not lowercase p, lowercase h. And that's because this lowercase p means it's telling us what to do. That lowercase p means take the negative log of what follows. What follows is my hydronium ion concentration. And so the pH of the solution would be the negative log of my hydronium ion concentration. And you might see it right the other way as well. pH is the negative log of just H+, because those two are the same thing. Now we can find the pH of a solution. So in pure water, we know my hydronium concentration is 1 times 10 to the minus 7, and we know our hydroxide concentration is also 1 times 10 to the minus 7. We can find the pH based on that. pH equals the negative log of 1 times 10 to the minus 7, and the pH of a neutral solution of a pure water solution would be 7.00. So in acidic solution, we're looking for something that has higher concentration then 1 times 10 to the minus 7. And that would make our pH less than 7. And in a basic solution, the opposite's going to happen. In a basic solution, our hydronium concentration goes down, our hydroxide goes up, and that's going to give us a pH of greater than . So for a neutral solution, 10 to the minus 7, 1 times 10 to the minus 7 is our concentration of both hydronium and hydroxide. For an acidic solution, hydronium concentration increases, and for a basic solution, my hydroxide concentration is going to increase. So here's one quick question for you. Calculate the pH of typical adult blood, which has a hydronium ion concentration. And remember, hydronium ion concentration is H3O plus of 4 times 10 to the minus 8 molar. All right, so the pH is the negative log of our hydronium ion concentration. So pH equals the negative log of 4 times 10 to the minus 8. And so pH equals 7.3979. Now for everyone's favorite topic, significant figures. For significant figures for this concentration, I have 2 significant figures there, so everything counts there. For pH, the only numbers that count toward your significant figures are the number after the decimal. So we need to have 2 significant figures after the decimal place. The leading number does not count. That's just telling you how far away you are from 0. So to report this with the correct numbers of significant figures, we're going to drop everything after the 3 and the 9. We're dropping a 7, so we would round this up to say pH of 7.40. 2 sig figs there to match the 2 significant figures we have there.